We have such a device in this Polaroid filter. As you can see, light is getting through the filter. What has happened is that the electric vibrations that get through are lined up with the axis of the Polaroid. I have another identical Polaroid filter, which I'll put in front of this one. And I have previously arranged the two axes so that they are parallel. Light is getting through both of them. Now, if I rotate the second axis by 90 degrees, I should expect to get much less intensity getting through to the screen. This is because the vibrations lined up with the first axis reach the second Polaroid and find there an axis at right angles to them, and therefore they should not get through. Let me rotate it and see what happens. The intensity has gone down. If I rotate it another 90 degrees, the intensity has gone up again. And this is what we expect, because now the vibrations lined up by the first Polaroid again meet a parallel axis and therefore get through. Now, it certainly can't be that most of the light is a longitudinal wave. That is, that the vibration lies along the direction of motion. Because if this were so, then the axis of the Polaroid would always be at right angles to the vibration, even when I rotate it. And so no one angle could make any difference, and the intensity should not be affected. So it must be that light is mostly transverse. And if we wanted to make the experiment more elaborate and could use a better Polaroid filter, I could show you that light is entirely transverse. I hope by this simple experiment that you now see that light can be polarized, that it is transverse, and that these two properties are closely related. Let's do an interference experiment in the X-ray region now. This is a typical X-ray tube. It has a very simple structure. This is a glass envelope which is evacuated when in use. There is a cathode at one end which emits electrons when heated. And at the other end, there is a copper plate or anode. A large positive voltage is put between plate and cathode, thus accelerating the electrons to the anode. When they arrive, they have a very high energy and collide with the anode. This violent deceleration causes the emission of electromagnetic waves. We call these waves X-rays. This is the apparatus we'll use for our X-ray interference experiment. There's an X-ray tube similar to the one you just saw in this metal can. The X-rays leave the tube here and strike a lithium fluoride crystal. The crystal looks like this and consists simply of lithium and fluorine ions in a regular cubic array. If you looked at the crystal end on, it would look something like this. The important idea to get from looking at this model is that the ions can be considered as lying in planes. And in our experiment, we are going to consider the reflection of electromagnetic waves from these planes of ions. By using the ripple tank, we can show how this reflection works. Each peg represents a row of ions in the crystal. Water waves will be generated moving towards the model. The incoming wave will successively reach each of the planes. Now, the angle at which the wave enters the crystal is important. If the incoming wave makes an angle with the plane, such that the re-radiated waves add up, crest on crest, then we get a strong reflected wave or constructive interference. And that's just what we have now. Notice that there is a distinct reflected wave leaving the model at the lower right of the screen. The condition for constructive interference involves the angle between the incoming wave and the crystal planes. Only at the correct angle will we get constructive interference. We are at this angle now, so let's mark the angle as a reference. If we change the angle, like this, the individual reflections mutually cancel, and we get a very weak reflected wave. When I again reach the correct angle, I get constructive interference, a strong reflected wave. In our X-ray experiment, we will be able to detect constructive interference with the lithium fluoride crystal. We can see the entire experiment on this diagram. The electron beam in the X-ray tube hits the anode, and X-rays are emitted. They strike the crystal at an angle theta, leave at the same angle, and enter a Geiger counter detector. The output of the Geiger counter is put on an electronic counter. What we will do in this experiment is to vary the angle theta and look for those special angles where we get constructive interference of the reflected waves. Now let's do the experiment. As I turn this dial, I am varying the angle theta between the incoming waves in the crystal and between the outgoing waves and the crystal. Notice both the lights on the electronic counter and the clicks. We get a click every 64 counts. The intensity is increasing, and I'll stop at a peak. This corresponds to constructive interference between the reflected waves. As I move off the peak, the intensity drops down. And I'll continue to vary the angle. Now we're coming to a second peak, and I'll stop at its maximum. Notice that we're getting interference phenomena, which, as you know, are characteristic of wave motion. We're going to do a microwave experiment now, which will be directly analogous to the Young's optical interference experiment you saw just a little while ago. Only in this case, the waves will have a frequency of 9,000 million cycles per second, corresponding to a wavelength of about 3.3 centimeters. We'll produce the microwaves in a tube called a klystron. Here's one. The microwaves come out from this antenna. We pump electric charge or current up and down this antenna, and the accelerated charge sends out the waves. We've got the same klystron in this metal can. The accelerated charges on the antenna start an electromagnetic wave down this pipe. The wave reaches this point and splits and arrives at these 2 points with identical phase. We then feed them through these 2 horns out into space. The purpose of the horns is to minimize reflections, which are caused when we make the transition between the pipe and the space. The 2 horns in this experiment will act just like the double slit did in the optics experiment. Here we have a detector, which is sensitive to the resultant electric field tangent to it. We're going to move the detector back and forth through space this way, thus sampling the total electric field resulting from both these horns at each point in space. The output of the detector will be fed to this meter. Now let's do the experiment. As I move the detector this way, across the incoming waves, you can see that the deflection on the meter goes through a series of maxima and minima. You can also hear it on a loudspeaker we've hooked up because we're chopping the microwaves 1,000 times a second. Just as in the optics experiment, when a crest from one horn meets a crest from the other, we get a constructive interference or a maximum at the detector. And when a crest from one horn meets a trough from the other, we get destructive interference or a minimum on the meter. In order to show that this is really an interference phenomenon, we have to show that both horns are simultaneously involved in producing the resultant field at the detector. Now you'll remember we stopped at a minimum. Let's close one of the horns and see what happens. The intensity on the meter went up. This means that the field from this horn can no longer cancel the field from the other. Let's go back to a maximum. And I'll again close one of the horns. In this case, the intensity on the meter went down. This was because we closed one of the horns, thus leaving only the intensity due to the other one. It's easy to show that microwaves can be polarized. If we place a screen like this between the horn and the detector, you can see that in this position the intensity on the meter is relatively unaffected. But if I rotate the screen by 90 degrees, the intensity on the meter drops almost to zero. The reason for this is that in the second position, the electric field was parallel to the wires. This set up strong currents in the wires, which converted much of the microwaves to heat. In the first case, the electric field was perpendicular to the wires, not much current flowed, and most of the microwaves got through. You have noticed that in this experiment, the microwaves were already polarized as they left the horns. The important thing is that we could polarize them, just as we were able to do with light in the optics experiment. And once they were polarized, they retained this property as they traveled through space. We showed you this when we placed the screen at some distance in front of the horn. This meant that the microwaves had to carry their polarization property with them as they traveled to the screen. Incidentally, it's easy to measure the wavelength of microwaves. If we place a reflecting screen behind the detector, we can pick up a standing wave pattern. And by measuring the distance between minima, we can get the wavelength of microwaves. Let's go do it. I'll put up a reflecting plate in back of the antenna. The wave coming out of the horn comes down this way and bounces off this plate. At the position of the antenna, we have both an incoming wave and a reflected wave. As you know, the sum of two such waves gives a standing wave. I'm going to move the antenna in this direction and follow its position with this pointer. In order to allow me to measure the standing waves, I'll put this centimeter stick behind it as a scale. As I move the antenna, we go through a minimum, maximum, and let me stop at a minimum and mark the scale. Now I'll move the antenna to the next minimum. And mark the scale again. The difference between these two marks is just 1.65 centimeters. As you know, standing wave minima occur every half wavelength. This means that the wavelength of these microwaves is twice 1.65, or 3.3 centimeters. The most common use of microwaves, radar, is probably familiar to most of you. In radar, we shine microwaves onto an object and measure the time it takes for the microwaves to go to it and come back. If we take half this time interval and multiply it by the speed with which microwaves travel, we can calculate the distance of the object. This speed turns out to be exactly equal to the speed of light. Our last experiment is in the radio wave part of the spectrum. Here we will work at a frequency of 140 million cycles per second, corresponding to a wavelength of about 2.1 meters. Because of this large wavelength, we obviously have to work with much larger physical apparatus and in a larger area. This large field will be perfect for our experiment. Aside from the larger equipment which we'll use and the lower frequency, this experiment will be identical to the one you saw with microwaves. There are two antennas set up about 20 feet apart, which in this experiment will take the place of the two horns in the microwave experiment. The antennas are fed from the same transmitter, thus making them coherent sources of electromagnetic waves. We're going to pick up the resultant electric field from the two antennas with a similar one here. The way the waves come out from these two sources is just the way the klystron antenna sent out microwaves. What we're doing is to pump electric charge from the transmitter into and out of the antennas and back and forth at the rate of 140 million times per second. It is this accelerated charge which sends our electromagnetic waves off. Now, if our ideas of the interference of electromagnetic waves are correct, we'd expect to find regions of constructive and destructive interference in the space here in front of the two sources. So what we're going to do is to move our pickup antenna back and forth in space, thus sampling the resultant electric field from the two sources. We'll convert the received signal into sound on this loudspeaker and also into a deflection on the meter. The reason you can hear the sound is because we're chopping the transmitter signal 1,000 times per second. Now let's try the experiment. As we roll along, moving the detector, once again, we go through a series of minima, maxima, and minima. Now let's try it again. And I'll stop at a minimum. To see that this is really an interference effect, let's disconnect one of the antennas. John, you see the intensity has gone up, both on the meter and in the sound level. This is because we've disconnected one antenna, and so it can no longer cancel the field due to the other. Let's reconnect it. Our intensity is down again. We're at a minimum or a point of destructive interference. Let's try the same thing at a maximum. And let's disconnect one of the antennas. Now you see the signal has dropped. This is because we removed an antenna, so we're receiving the field due to only one. And so we get a smaller signal. So you see, once again we have wave interference, this time in the radio wave region of the electromagnetic spectrum. There's one more wave property I want to show you, and that is that radio waves are polarized. The waves being transmitted by our antennas are polarized such that the electric disturbance is parallel to the metal rod or antenna. This is because we're pumping charge or accelerating it back and forth along the rod, and it is this accelerated charge which starts the wave going parallel to the rod. We can show the polarization of these waves as actually received by rotating the antenna. John, would you rotate it by 90 degrees? You see, as he rotates it, the intensity drops, and at 90 degrees, it has gone down to 0. This is because the antenna is now sending a radio wave polarized such that the electric field is perpendicular to the antenna that is receiving it. Because they are perpendicular, you get a minimum received signal. Let's rotate it by another 90 degrees and see what happens. You see, the intensity has gone up again. This is because the two antennas are again parallel. The wave being transmitted is polarized such that it arrives at the receiving antenna with its electric disturbance parallel to the antenna and is now fully received. Let's see what we have accomplished. By doing a simple interference experiment in 4 widely separated regions of the electromagnetic spectrum, I've been able to show you that the interference effects arise from waves, that the waves are transverse and can be polarized, that they arise from accelerated charges and travel with the speed of light. It is due to these common properties that we believe in the unity of the electromagnetic spectrum.
You're in flap lags and whipping clotheslines, but I'll bet you hardly ever seen it happen this slow before. In the classroom and in the laboratory, you have been studying the properties of pulses and waves. In this film, I want to show you in more detail some of the wave properties that are pictured and discussed in the text. I hope that by seeing actually how waves behave in various situations, you will be able to understand them better. This steel spring is very similar to the slinky that you have used in the laboratory. I can launch a pulse on it simply by giving my wrist a quick flip. Any pulse I generate has certain properties. It has a size and a shape and a speed along the spring. Perhaps you can see these features better in slow motion. Note that at any point on the spring, the medium is at rest both before the wave arrives and after the wave has passed by. Down at the other end of the table, where the spring is rigidly fastened, the pulse is reflected back toward my hand. Note also that after a few such reflections, the wave dies out. This dying out is due mainly to the friction which the tabletop exerts against the crosswise motion of the coils of the spring. Now, there are a number of fundamental properties possessed by waves of all kinds, which it is important for us to know about and to understand. And I've devised a number of simple experiments here which should lead us to some fairly definite conclusions about these fundamentals. Now, just what is it that we wish to know? Well, first, does the speed of a wave depend upon the nature of the medium it is traveling in? Or to put it in other words, will waves travel in different media with different speeds? Second, will a wave travel with a constant speed in a uniform medium? And third, How does the speed of a wave or pulse depend upon its size or upon its shape? Now let's concentrate our attention on the first of these three questions. Does the speed of a wave depend on the properties of the medium it is traveling in? Here I have three different things. A small diameter brass spring, the slinky that I have used in previous experiments, and a long piece of heavy wall rubber tube. Each of these three things can be used as a medium for the propagation of waves. This crosspiece will enable me to launch pulses on all three of these things at the same time. Pulses travel with different speeds, don't they? Here, let me launch a few more while you watch them in slow motion. Let's watch that again. You see, this experiment answers our question, doesn't it? The speed of a pulse depends on the nature of the medium it is traveling in. Now let's think about our second question. In a uniform medium, is the speed of a wave constant? Say, will you take care of these for me, please? What I want to do now is to study the motion of a pulse along this brass spring by taking 6 flash photographs of a single pulse as it travels along. Doing this will give me a picture showing the 6 instantaneous positions of the pulse at 5 equally spaced intervals of time, all as a multiple exposure, you see, on the same picture. In this picture, I shall be able to determine the 6 positions of the pulse by interpolating between the lines on the tabletop. These marks are 50 centimeters apart. The spring itself is made of brass wire of uniform diameter. The spring has a constant number of turns per centimeter, and in the experiment it will be held under uniform tension so that it can be considered to be a uniform medium. Now let's have a look at the apparatus I'm going to use to fire off the flash bulbs. This is a rotating switch turned by an old phonograph motor, which will close an electric circuit to the 6 flash bulbs, one after the other, at intervals of 1/20th of a second. Now, we don't want any of those flash bulbs to go off before the pulse is launched on its way, so I have included in that battery circuit a master switch, a mousetrap, which will be set off by the pulse itself, by the pull of this white thread, when the pulse has reached this position on the table. All right, now that everything seems ready, I'll darken the room, and my assistant will open the camera shutter, and I'll start the pulse on its way. All right, ready? 5, 4, 3, 2, 1, 0. Here is an enlargement of that flash picture we took a little while ago. Let's look at it and analyze it for what information we can extract from it. In it, you can clearly see the positions the pulse occupied at each of the 6 flashes. 1, 2, 3, 4, 5, 6. Oh, and here also is evidence that the pulse was dying out as it traveled along. Look, the size of the pulse at this end of the table is noticeably smaller than it was up here when the first flash went off. All right, granted the dying out, now what about the speed? I could go to some trouble to analyze this picture and carefully determine where, say, the middle of the pulse was at each flash. However, I don't think doing this will be necessary, for I believe you can see with half an eye that the pulse positions are equally spaced and that in each 1/20th second interval, the pulse advanced about 50 centimeters. There is no evidence in this picture for either speeding up or slowing down, and we may therefore conclude that at least within the limits of our simple observation, the pulse traveled with substantially constant speed. The size of the pulse was dying out, to be sure, but its speed remained constant. Now, so far we have demonstrated that waves travel with different speeds in different media, and that a wave travels with constant speed in a uniform medium. With these facts established, we should be able to predict that equal waves in equal media should travel with equal speeds. Let's see if this is really true. Here are two slinkies, as identical as it is possible to make them, both pulled out to the same tension. I'm going to launch identical pulses on these two slinkies, and you watch what happens to them. They traveled side by side, didn't they? Let me do it again. Now let's watch that all over again in slow motion. Now I'm going to make you think a little. Suppose I reach out and gather in a few turns of the right-hand slinky so as to stretch the remainder tighter than it was before. Is there any reason to believe that the speed of a pulse will be any different under this new condition? It's the same slinky. Is it? After all, I have stretched it tighter and changed its condition. Well, will a pulse travel faster or slower or with the same speed as before? This test will give us the answer. Watch now. Now let's watch that all over again in slow motion. Well, there's no doubt about it. The pulse traveled faster on the tighter slinky. Now let's watch that again. Evidently, the wave depends not only on the medium it is traveling in, but also on the condition of that medium as well. For example, here, when I tightened up this, I changed its condition by increasing its tension. So I changed the speed of a pulse along it. Now I'm going to ask my assistant to get rid of these slinkies for me and bring me that rubber tube that I was playing with before. This is the same piece of thick-walled rubber tube that you saw in an earlier experiment. Perhaps you noticed that it has a black stripe painted down one side. Now this time, instead of giving my wrist a quick flip so as to generate a transverse pulse traveling down this tube, I'm going to give the end of it a quick twist, generating a wave of twist which travels down and which I hope you will be able to follow by observing the behavior of the black stripe. Watch this. Well, that pulse traveled awfully fast, didn't it? And I question how much of it you could really see in any detail. So I suggest that we have a look at a different kind of twist wave apparatus. This rod behaves very much like the rubber tube we were just looking at. In order that you may follow the progress of a pulse along its length, I have soldered a number of cross arms between its two ends. These cross arms make the pulse travel more slowly. This thing down here is simply a tin can full of water with a little piston pumping up and down in it. That piston is attached to the end cross arm so as to prevent that cross arm from overshooting when a pulse comes along. Now, if I twist one end of this rod by simply displacing the cross arm in my hand, that pulse of twist travels down the length of the rod and displaces this cross arm in turn. The speed of a pulse on this steel rod, of course, is very fast, and it may have seemed to you just now that the action was almost instantaneous. However, I'm going to repeat these pulses at periodic intervals, and if you watch carefully, you will be able to note that there is a time lag between the displacement of the cross arm in my hand and the resulting displacement of the cross arm at the other end. This time lag is precisely the time it takes for a wave to travel the length of this rod. Now let's have a look at still another wave machine. This one is very much like the one I was just playing with, except, as you see, it has a larger number of cross arms spaced at equal intervals between its two ends. The central rod, that is the backbone of this beautiful structure, is resting in bearings which permit it to twist freely. Remember now, it's this central rod that is behaving like the rubber tube in the last shot. The speed of a pulse along this rod is very fast because steel is much stiffer than rubber, and in order to slow the pulse down, these cross arms have been added. It will be difficult for you to see the progress of the pulse along the central arm, and therefore it'll be necessary for you to observe the progressive displacement of the ends of these cross arms as the pulse itself travels along the central rod. Now I'm going to produce a twist of the central rod by giving this cross arm an up and down motion. Now watch. Isn't that simply fascinating? You observe that the pulse traveled the entire length of the machine, was reflected at the far end, came back again and was reflected at this end, and repeated back and forth many times. Of course, it eventually dies out, and you've seen examples of this dying out before, in the case, for instance, of the slinky on the tabletop. This machine has a lot less friction, however, than the slinky, and it's not surprising, therefore, that the pulse lasted a great deal longer before it eventually died away. Now I wonder if you wouldn't like to see this thing happening again in slow motion. And the next thing that you see will be another pulse, which I will start, traveling along the machine at about half the normal speed. Here goes. This is a very handy piece of apparatus for studying the behavior of waves. Let's use it, therefore, to answer our third question. Does the speed of a wave depend on its size or its shape? Thank you. On this apparatus, a wave travels slow enough so that I can get a reliable determination of its speed simply by measuring with this stop clock how long it takes the wave to make a round trip down and back. Let's try it. Here goes. Start. Stop. That took 4.0 seconds. Let me do it again just to get confirmation. Here we go in slow motion. Start. Stop. That took 3.9 seconds, about the same as before. Now let's study the behavior of a pulse which is noticeably smaller than the two I just launched. Here we go. Start. Stop. That took 4.0 seconds, and I'll do this one again, too, just to make sure. in slow motion. Start. Stop. That took 3.9 seconds, about the same as before. Well, this is interesting. Apparently, the size of a wave has little effect on the speed with which it travels. Now let's study a wave of different shape. So far, the pulses we have been using have been little short pulses, maybe 5 or 6 inches long. Let's now launch a pulse which is half the length of the entire machine and see how that travels. Here we go. Start. Stop. That took 3.8 seconds, substantially the same as before. Let's do this one again, too, just to be sure. This time in slow motion. Start. Stop. 4.0, same as all the others. Well, now this is an interesting development, isn't it? Here we have a wave medium on which waves of all kinds, regardless of size and shape, seem to travel with substantially the same speed. Nature abounds with this kind of wave behavior. For example, when you're listening to a band playing on a football field between halves, the sound waves of various sizes and shapes, which correspond to the different pitches and loudnesses of the music you're listening to, all reach your ear with the same relative timing as when they left the instruments down on the field. Now let's examine a few other aspects of wave behavior. Here is a second wave propagation machine. It is similar to that one, except that the cross arms are only about half as long. It is therefore physically a different medium, and we would expect the speeds of waves to be different in the two. This difference I can show you quite dramatically if I mount the second machine over the first and, with the aid of this little wire connector, launch pulses on both media simultaneously in slow motion. Watch now. Well, there's no doubt about that. The pulse travels a lot faster in the medium with shorter cross arms. This observation is quite in keeping with what we have already learned in other experiments. Waves travel in different media with different speeds. Now let me show you something else. Here I have placed the second machine end to end with the first machine, and I am now going to clamp their central rods rigidly together. This little clip will do it. Now what do you think will happen to a pulse as it travels along the first machine and crosses the boundary into the second? It should slow down, shouldn't it? In any medium, a wave travels with a speed which is characteristic of that medium. Therefore, as a wave comes along and crosses this boundary, we expect that it will change its speed. Now let's see if it really does. Watch carefully. There, did you see that? Did you see that as the wave crossed the boundary into the second medium, it did indeed change speed? I'll bet you'd like to see that again in slow motion. Watch now. Isn't that simply beautiful? But wait a minute. Have we seen everything there is to see? Did you notice that as the wave crossed the boundary, it was not only partly transmitted into the second machine, but it was also partly reflected back again onto the first machine? I'm going to repeat this experiment again in slow motion while you watch carefully for the reflected pulse. Watch now. Evidently then, when a wave crosses a boundary between two dissimilar media, it is partly reflected and partly transmitted. Now, have you ever seen behavior of this kind before? I'm sure you have. You know that when a beam of light passes from air into glass or water, it is partly transmitted and partly reflected at the surface. In this respect, at least, light behaves much as waves behave on our mechanical models. And the farther you go in your studies of physics, the more similarities of this kind you will find between the behaviors of all sorts of wave. Now let's review the things that we have been studying. The speed of a wave depends on the properties of the material in which it travels. In different materials, the speed of a wave will, in general, be different. Even in the same material, changing the conditions will cause a change of speed, and thus the same material may become a different medium. In a uniform medium, the speed of a wave is constant. This we showed by demonstrating that a wave on a uniform medium traveled equal distances in equal intervals of time. While transverse and longitudinal waves are commonplace, waves of twist also occur. In many cases, the speed of a wave is independent of its size or shape. When a wave encounters a boundary between two different materials, it is partly transmitted across the boundary into the second and partly reflected back into the first. We are going to need to know a great deal more about wave behavior as we progress in this course, and later on we shall spend a good deal of time in such studies in other films.
So you already know that sound travels at a finite speed. It travels at a speed that you can sense for yourself. And of course, if you want to, you can go about measuring it. It's really quite simple. Particularly, you find the sound, stand a few hundred yards away, clap your hands sharply, measure the time it takes for the sound to come back to you, and then measure your distance from the reflecting surface.
A water ripple makes a good model of an echo.
Well, if you do this a number of times, you'll find that in air, sound travels a little more than 1,100 feet per second, or about 340 meters per second. Now, an echo is simply reflected sound. In order to find out whether the angles for reflected sound obey the same law that we found for reflected light, we're going to need a beam of sound and a suitable laboratory in which to use it. Now, this studio is not an ideal sound laboratory, but we have taken a number of precautions here to minimize the stray reflections. For example, these are glass fiber blankets that absorb most of the sound that strikes them. And the floor is covered with thick felt pads. Without these precautions, we wouldn't be able to separate the sounds we are going to study from the many extraneous reflections from the furniture, the ceiling, the walls, and the floor. Now, our sound is going to be produced by this equipment over here. We'll generate the tone in this oscillator. And we can have a range of higher tones or lower tones. And, of course, we can also adjust the intensity up or down to suit our needs. Now, the electrical output from this oscillator is amplified over here, and then it activates a loudspeaker driver. And the sound produced in this loudspeaker driver is fed into the throat of this horn. Of course, we could just hold the loudspeaker driver out in the open, but then the sound would go out in all directions, like the light from a candle flame. When the driver is attached to this exponential horn, most of the sound goes out along the axis. Of course, we can hear a little sound all around, but over here in front, it should be very much louder. Let me listen. Yes, there's a good, strong concentration right here. And so that you can hear what I hear, we've set up this special microphone. And we've mounted this meter near the mic so that you can see the changes in sound intensity as well as hear them. Now let's see what kind of beam this horn is giving us. First, we'll turn on the microphone. So, as you could see and hear, we've got a really good, strong beam of sound to work with. Now let's put a reflector in the way. I'll put the mic over here first, and then push this baffle around to put the hard side in the beam. Now we have the beam of sound from the loudspeaker coming out in this direction. It strikes the central portion of the reflector and then goes off in this general direction. Let's try to locate the reflected beam. And to do that with some degree of accuracy, we'll use the microphone and meter, and then you can listen and watch at the same time. I'm going to move this back and forth through the general region where we expect the beam to be, and once we locate the center, we'll hang the microphone on the stand located at that point. that looks pretty good. Let me just turn it on again for a moment and see if we really have it up near the top of the scale. Okay, so now we've located the reflected beam, and we know that it goes out in this direction and is centered approximately at the microphone. However, we're still assuming that the sound is going through this path and along this path to the microphone. Let's see if we can't check that more rigorously. And here's one way to do it. I'll use this as a shield and intercept the reflected beam. Of course, when I do this, the sound should drop and the meter should go down. And of course, I can also intercept the direct beam or even put the shield right here where the two beams come together at the reflector. Well, I think you'll agree that's fairly convincing evidence that the sound is really traveling along these paths as we expected. But we haven't really asked the key question yet. Is this angle of reflection equal to the angle of incidence? Here's a quick way to find out. Looking past the microphone and into the mirror, you can see that the microphone lines up with the axis of the horn. So the sound and the light do follow the same path. Now let's sum up a bit. We've shown that sound travels in straight lines and reflects, and that the angle of reflection is equal to the angle of incidence. Now, of course, particles do this when they bounce off of a reflector. But also, waves behave the same way, as we've already seen with light and with water ripples. So which do we have here, particles or waves? Well, for one thing, waves bend around corners, whereas particles normally go straight ahead. Waves diffract. They spread out through narrow openings. And they spread in behind obstacles. And waves spread around the ends of barriers. We know from common experience that sound bends around corners. Let me turn this microphone on so that now you'll be hearing my voice only through this microphone. And I'm going to walk around behind our baffle and keep talking to you. Now, of course, you still hear my voice, though it's a little bit weaker. And this makes it obvious that the sound from my voice is indeed bending around this baffle in order to get back to the microphone. Well, from this point of view, it certainly seems clear that we are dealing with waves and not with particles. But there are many other characteristics of waves that you know about, so why don't we try to tie this question down more firmly? Now, a very basic test for waves is to look for an interference pattern. A good example of interference is a standing wave, such as we ought to be able to establish in front of this baffle. So let me pull it around. There, the baffle is now at about 90 degrees to the beam of sound from our horn, and we should be able to establish a standing wave here. But before we do that, let's go back and take a look again at a model of a standing wave. Now, if I send out a wave pulse, it reflects from the other end. And if I send out a continuous train of waves, the reflected waves interfere with the incident waves, and we get regions of maximum displacement and regions of minimum displacement. The regions of minimum displacement are the displacement nodes. Now let's see if we can get the same pattern in our beam of sound. We'll set up a tone on our oscillator, and this time we'll use a lower tone than we did before. Now we have our sound beam from the horn striking the baffle at right angles, and we want to explore the sound field out here in front. So we'll use our microphone and see if we can find maxima and minima. Well, clearly we have maxima and minima. Now let's measure the positions of these minima in the wave pattern. And to do that, I'll bring over a marker and place it along the axis of the sound beam and perpendicular to the baffle. And I'll turn the microphone on again. Well, I'm sure you'll agree that we had sharp nodes at these points that we've marked. The sound level dropped abruptly, and the meter went down to the bottom of the scale. So the evidence is mounting that we do have a standing wave here, that this is an interference pattern, and inevitably that sound is a wave phenomenon. Well, if so, there's some other things that we can check right away. For one thing, as you know, in an interference pattern, the dimensions depend upon wavelength. And in this special case of a simple standing wave, the distances between the adjacent nodes are equal to a half wavelength. So let's measure these distances. The first one is about 52 centimeters. And the second one is about 50 centimeters. Well, those are equal within the accuracy of our quick check. So we can take the half wavelength as having an average value of about 51 centimeters, which gives us a wavelength of about 102 centimeters, or lambda is 1.02 meters. We've already mentioned that the speed of sound in air is 340 meters per second. Now let's calculate the frequency. You remember the formula for frequency is equal to the speed divided by the wavelength. Incidentally, there's a nice way to visualize this formula physically. If you think of a train of waves going by you, and the length of that train that goes by in 1 second is simply the speed, then you divide that by the length of a single wave, and obviously you have the number of waves per second or the number of cycles per second. All right, in this case, the frequency is equal to 340 divided by 1.02, and that is equal to 333 cycles per second. Well, we've calculated the frequency from our measurement. Well, let's see how this checks with the dial on the oscillator. This reads just over 33 times 10, so the frequency is set at just over 330 cycles per second. That checks very nicely. Now, what about this oscillator? Well, we can calibrate it independently. With an oscilloscope, it's very easy to spread the vibrations out in space using an appropriate sweep speed. For example, we established a tone of 1,000 cycles per second on the oscillator and selected a sweep of 1/100th of a second and then counted exactly 10 vibrations across the face of the scope. Well, we did this at a number of frequencies, and the calibrations all checked out quite nicely. Now, if we select a higher frequency, what will happen to our wavelengths? Well, let's do that. Let's multiply the frequency by 10. To do that, we don't have to change the dial at all. We simply throw the range scale by a factor of 10. So now we've increased our frequency by a factor of 10. We should have cut our wavelength to 1/10. Let's mark the positions of the nodes with this higher frequency. I'll turn on the microphone. And let's count how many we have. Starting a little bit to the right of the mark we had before, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, within reasonable accuracy, we've obtained 10 nodal points, or 10 half wavelengths, where before we had just one. And this, of course, shows that our wavelength has gone down by a factor of 10 when we increased our frequency by a factor of 10. Now, one interference effect might conceivably be an accident. There's another familiar one that we can try. You've used a grating to obtain interference with light and with waves in a ripple tank. This is an interference pattern beyond the grating, a transmitted pattern. And this is the reflected pattern produced by a grating. Notice the antinode holding steady in this direction, and the nodes here and here. If we were to investigate this pattern along an arc like this, we would pick up regions of minimum displacement alternating with regions of maximum displacement. We would be observing a cross-section of this interference pattern. We can do a grating experiment with sound using a similar geometry. A grating, a source of sound, a receiver with which to explore along an arc about the grating, and a baffle to block direct transmission between the source and the receiver. Over here we have our source horn with the beam of sound coming off in this direction. And here we have a grating that we've made from dowels placed 15 centimeters apart from center to center. You can make one easily with some old broom handles. We've placed the plane of the grating at right angles to the beam of sound. And over here we have another horn, a receiver horn. As you see, we've inserted our microphone into the throat of this horn, and this gives us a sharply directional receiver to pick up the rather weak sound that's reflected from the grating, and also to discriminate against sound from other parts of the room. Now, this wire along here pivots the receiving horn about the center point of the grating so that we can move this horn along the arc here and always keep it pointed right at the grating. Now let's set up a tone on our oscillator. And we've picked 5,000 cycles per second this time. Now let's start by looking for a maximum in the wave pattern. So I'll turn on the microphone. There we found a good strong maximum and marked it. But you noticed right near that maximum, there was a secondary maximum. Now, actually, this is the sort of thing we should expect because we have a rather small grating. It's got only 7 elements, whereas an optical grating normally has thousands of scattering elements. And because of its finite size, this grating produces a secondary interference pattern that's superimposed on top of the primary interference pattern. The primary pattern is the one that's determined only by the spacing between the elements and the wavelength. So as I continue to explore this sound field, I'll try to pick out only the highest maximum and the lowest minimum. In other words, I'll try to mark only the primary interference pattern. Well, now you can really visualize this interference pattern produced by our grating. You see spread out along this arc two strong maxima and a sharp minimum or node in between. Actually, as you know, there's another minimum over here closer to the sound beam, but it lies right along our baffle, so you can't observe it. Now, that would be our first minimum. This is the first maximum. Over here is the second minimum, or second node, and out here we've marked the second maximum. This is a very well-defined interference pattern, but one that's quite different from the standing wave we observed in front of the reflector. So here we have strong, independent evidence that sound is a wave phenomenon. Now there's something you can calculate. This second node is located at an angle of 43 degrees from the axis of the incident sound beam. And that axis, you remember, is at right angles to the plane of the grating. And the elements of the grating are spaced about 15 centimeters apart from center to center. So from this information, you can calculate the wavelength of the sound we've just used. But also, you've got a new way to calculate the speed of sound. Remember, we used a frequency of 5,000 cycles per second. And using that number and the wavelength you've just calculated, you can find out the speed of sound in this room today. Now there's just one thing we've omitted from the usual list of wave properties. When waves pass from one medium to another, you often see a change of direction, or refraction. A change in the depth of the water in your ripple tank gave you a model of two different media. If you give the shallow area a special shape, a lens shape, the refraction of waves through the lens produces a focusing effect on the waves, concentrating them in this small region. With this double convex lens, we're going to try to refract sound, to focus sound waves. This lens is made of carbon dioxide gas coated on both sides with thin plastic sheets. The carbon dioxide is pumped up to a little more than atmospheric pressure in order to maintain the shapes of the lens surfaces. Our beam of sound is directed at the center of the lens right here, so we expect to find the focus out in this direction. Let's use the frequency of 5,000 cycles again. The screen here is almost perfectly transparent to sound, and it's located right where we expect to find the focal pattern. So let's explore this region with our microphone and observe the changes in sound intensity as we go through it. Now, just so we can keep a record of what we observe, each time the meter needle reads 70, I'll put a marker on the screen. Everywhere within this circle, the meter reading is more than 70. Well, that looks like a satisfactory focal pattern, but how can we be sure that we aren't simply measuring the cross-section of the beam directly from the horn? I'll hang the microphone here at the center of our focus, and then go and take the lens away so that nothing will stand between the loudspeaker and the microphone. And while I do this, you watch the meter. Well, our lens works. We've observed the refraction of sound through carbon dioxide. Now, what have we learned about sound? We've seen that the angle of reflection equals the angle of incidence. We've heard the diffraction of sound around the edge of a barrier. We've observed the interference pattern in the standing wave in front of a reflector. And we've noted that speed equals frequency times wavelength for sound as it does for other waves. We've observed another interference pattern of nodes and antinodes produced by a grating. And here we've observed the refraction of sound. So now we know that sound is transmitted by waves and that its behavior is predictable by the same wave theory we've already learned.
This is the way we usually arrive at the inverse square law of gravitation. You assume that the planets move around in circles with the sun at the center. Then you use Newton's law of motion, F equals ma. Next, you use one of Kepler's laws, the one that says that the period square is proportional to the radius cubed. Then, with a little simple algebra, you soon arrive at the relation that the force is inversely proportional to the square of the distance. Now, you and I know that all Earth satellites actually move in elliptical paths, and so do the planets. Today, we can get quickly the kind of data that Kepler got so painstakingly from Tycho's observations. In both cases, the story is the same. The planets or the Earth satellites move in elliptical paths. So it should be possible to arrive at the inverse square law from an ellipse. Now suppose we consider an Earth satellite moving in an elliptical path. Incidentally, Kepler was the first to realize that the planets move in elliptical paths with the sun at one focus. In this case, here, the Earth satellite moves in an elliptical path with the Earth at one focus. This is the logic I propose to follow. Once again, I will use F equals ma. This time, with special emphasis on the fact that both the force and the acceleration are vectors. Now, instead of using this, I will use another of Kepler's laws, the one that says that the radius vector sweeps out equal areas in equal times. This law, like all three of Kepler's laws, is based on direct observation of the planets. But today we get the relationship from observation of the satellites. It holds for Earth satellites and planets. Now we want to show how the inverse square law from this sequence of thoughts. Now, there is a basic difference between these two cases. A circle has a fixed radius, and so we have to go to different planets in order to sample the gravitational pull at different distances. On the other hand, within a single ellipse, the radius vector keeps changing in size, sampling, so to speak, the gravitational pull at different distances, even within one revolution. Well, this is what we have to do. Here's a satellite moving in an orbit. The Earth is here. We want to sample the gravitational force on the satellite here, here, and here. Now, one way to measure forces is to reason back from acceleration. If I can figure out how much the satellite will accelerate in a given time when it starts here, and how much it will accelerate in the same time when it starts here or here, I'll have a way of comparing forces. Now, in order to do that, I need a way of comparing times. I want to be sure that the time interval remains the same in all three cases. Well, I have a way of measuring time intervals. Kepler's second law. Equal areas in equal times. If I can move this area from here over to here, then the time required for the satellite to move this distance will be the same as this time, or this. Now, obviously, I'll need a more accurate ellipse if I'm going to get significant measurements from it. Well, that's exactly what we'll do. I will use Kepler's second law to be sure my time intervals are right. And then we'll see whether or not we can arrive at an inverse square law of gravitation. By using a carefully drawn ellipse, by analyzing the motion of a single Earth satellite, or any other body moving under the action of a central gravitational pull, as it moves in an elliptical path. Here's an ellipse. Now pretend the Earth is at a focus here. And imagine the Earth satellite moving around in an orbit like this. Now what I want to do is to sample the Earth's gravitational pull at three different places. Here, here, and here. And this is the way we'll do it. I will choose an arbitrary point on the ellipse at a distance r. I have that distance already notched on my ruler. And then at a distance 2r, where I have another notch. And a third notch at 3r. Like that. Now, if it weren't for the pull of gravity, the satellite would want to fly off along a tangent, like that. One way to draw a tangent line is to use the focal property of the ellipse. I can get my two radius vectors by using a string. When the mirror is tangent to the ellipse, the reflection of one radius vector looks like an extension of the other. So, if there were no gravity, the satellite would want to fly off along this line. Now my proof requires two other tangent lines. One at 2r. Where I repeat the process. second tangent line. And the last one at 3R. And there I have my 3 tangent lines. Now remember, if there were no gravity, the satellite would go that way, or that way, or that way. It's the pull of gravity that keeps the satellite in its orbit. But at this point, it is 3 times as far from the Earth as it was here. So the pull of gravity is weaker. How much weaker? That's what we want to find out. Well, suppose the satellite moved from here to here in an arbitrary time. Let's call that time t. The radius vector would sweep out a corresponding area. This area. The radius vector would move from here to here, sweeping out this area. Now take a look at this vector. The one that goes along the tangent line represents the distance the satellite would move in the arbitrary time t if there were no gravity. And this little vector, pointing along the radius toward the center of the Earth, is the distance that the satellite would fall towards the Earth in the same interval of time t. Now consider this point. How far would the satellite move in the same interval of time t, starting from here? Well, this is where I need the law of areas. I need some way of transferring this area over to here. I can do it this way. I've put just enough pellets in the beaker to fill the area. Now, it's quite obvious that if the pellets don't climb on top of one another, I have a quick way here of filling an area. I'll put a mark here at the end of this radial line. Now, if I don't lose any pellets or gain any, I can transfer this whole total area to this region. In order to do so, I have to open up my arc. It's not as easy as it looks. Obviously, this isn't the first time I've done it. Once again, I'll put a pencil mark at the end of this radial line. Now I'll move over to the third area. This time I have to open up the arc quite a bit. There's my third radial line. And now I have the marks I want, so I can get rid of my pellets. Now remember the meaning of this vector, the one along the tangent line here. This is the distance a satellite would travel in a time t if there were no gravity acting. And this is the distance the satellite would fall towards the center of the Earth in the same time t. This is velocity times time. But because this is the third tangent, I will call this v sub 3. And this is 1/2 at squared. Similarly, I will call this a sub 3. Using similar notation, this vector is v sub 2t. And this vector is 1/2 a sub 2 t squared. This vector is longer than the other acceleration vector. Now moving over into this position, it's apparent that this vector is much larger than the acceleration vectors we have seen. I will call this 1/2 a sub 1 t squared. And the one along the tangent, v sub 1 t. Now I have three acceleration vectors, and I'm in a position to answer the question, how much is the acceleration changing? I can make the comparison this way. This acceleration vector is this long, and it fits into this one 1, 2, 3, 4 times. So this acceleration is 4 times larger than this one. I'll call this one 1, and this one 1/4. Once again, let me measure this acceleration vector. And see how it fits into the original one. 1, 2, 3, 4, 5, 6, 7, 8, 9 times. This vector is 9 times as large as this one. So I'll mark this one 1/9. Well, that does it. When I doubled the distance, the acceleration became 1/4 of the original value. When I tripled the distance, the acceleration became 1/9 of its original value. Now, since force is directly proportional to acceleration, everything that I've said about acceleration holds true for force. And that makes an inverse square law of force seem very plausible. Now, I used 1, 2, and 3R, but I might have used a value like 2.65R. I assure you, the inverse square law would hold there, too. Now, I hope you understand what I've done and why I've done it. You might object that this is an approximate method only. This is true, but the approximations get better and better as the areas get smaller and smaller. In any graphical proof of this type, you have to make a compromise. You have to make the areas large enough so you can see them, and you have to make it small enough so that the radius vector does not change very much in direction or in magnitude. Well, you might wonder why I tried a proof of this sort instead of this. For years, the books have used this law and circular orbits to arrive at the inverse square law. But today, everybody knows that Earth satellites move in elliptical orbits. Of course, the planets also move in elliptical orbits, but they are so nearly circular that you can get by with this sort of a proof, and there's nothing wrong with it as far as it goes. But I wanted a proof that started off with an elliptical path. Now, make no mistake about it. If you repeat this construction and understand the significance of every step that you take, you will really understand the inverse square law and the motion of satellites.